the Academy for this kind invitation to give this talk. Okay, so we'll begin with some brief comments about general relativity and black holes. So let's start with the very familiar Newton's law of gravitation, which you all know from undergraduate college. That forces act instantaneously at a distance. This is the famous inverse square law. It's always attractive. And if you apply Newton's law of motion to this interaction of two bodies interacting by the gravitational field, then you can understand the elliptical orbits of planets which were described by Kepler. Now, this law is, as we know from hindsight, valid when the velocities of these moving objects are much smaller than the speed of light. All right, so next, let's jump a couple of 100 years. And in 1865, James Clerk Maxwell unified electricity and magnetism and demonstrated that the interaction between charges are communicated, not action at a distance, by the electromagnetic field, which propagates at the speed of light, finite speed of light. And in 1905, Einstein used this discovery to deduce that the speed of light is the same for all observers in relative motion, and hence there can be no action at a distance, which is simultaneous for observers in relative motion. So this is somehow in 3 lines the gist of this special theory of relativity. You'll forgive me for that, but I have a long way to go. So Newton's law of gravitation needs to be modified. So this is the main question Einstein arrived at towards the end of 1905, around 1907. And waging one of the great struggles in modern scientific history in 1915, Einstein completed the general theory of relativity, which is a theory of gravity in which the force of gravity is not instantaneous. It is communicated at a finite speed, the same speed, c, by changes in the geometry of space-time. And here, the role of the electromagnetic field is played by the metric of space-time, which tells you about how space-time is deformed by matter. And very simply, in one slide, what is the general theory of relativity? It describes changes of the geometry of space-time caused by massive objects to which other objects respond. And you might wonder actually why the space-time around you is not jiggling around. It's elastic, but it's a very stiff elastic grid, approximately 10 to the 20 times stiffer than steel. This is why you don't see gravitational waves popping all around you. Now, in a curved space-time, an object follows a path that maximizes the proper time in the frame of the object. And I just wanted to show you this very simple animation. All animations in this talk are due to Juan Maldacena. I just want to say it from the very beginning. So this ball, this sun, or very massive object, actually warps space-time. So it's like a trampoline which is being depressed. And the Earth, a smaller object, actually just follows this deformation actually in a particular way. So this summarizes the general theory of relativity and how objects move in it, okay? Now let's come to black holes, which is the centerpiece of our talk. So black holes are solutions of Einstein's equations, and I have not mentioned Einstein's equations because I don't think in this talk it's necessary to know. It'll just look like some piece of art actually, but you can just look it up anywhere. That black holes are solutions of Einstein's equations, and this exact solution of Einstein's equation was found by Carl Schwarzschild in 1916. And it has a very particular property actually, that it divides space-time into 2 parts. interior and exterior, separated by a surface which is called the horizon. And the horizon in classical physics, in classical general relativity, is a one-way gate. You get inside, you cannot get out. Even light entering it cannot get out, and hence the name black hole. The black hole space-time has a curvature singularity in the interior. So here is a picture, a cartoon. There are lots of cartoons in this talk of what a black hole is. So it's, as I said, a solution that divides space-time into two parts, the interior and the exterior of the horizon. And the interior has a singularity about which we will have nothing to say in this talk. So here is a picture of a collapsing star forming a black hole. So matter collapses, and under very general conditions, Roger Penrose had argued that a horizon would form, and this formation is quite a robust prediction of the general theory of relativity. So if you see, what happens is that after a while, the matter just falls in, and we are left with this object, this space-time I'm talking about, with the interior is colored black here and the exterior yellowish. And here is the horizon, the red line. So the horizon separates the space-time into these two parts. Now, the horizon is a null surface. That means, light rays just propagate just along it. These are all technicalities, which are not important for this talk, but there is a scale, there's a length scale in this theory, which is formed by Newton's coupling, the mass of the black hole, and divided by the speed of light squared. And this scale is called a Schwarzschild radius. Okay, so it's the radius of the black hole. Means inside the radius is the interior, outside the radius is the exterior. And because you have a radius in a spherically symmetric geometry, there is an area of this horizon, and which is just 4 pi r square from elementary Euclidean geometry. And note, it goes proportional to the square of the mass of the black hole. Okay, so there is an area. So this is our central object of this talk, the area of the horizon of the black hole. Okay, and it goes in this particular spherically symmetric black hole as just the square of the mass of the black hole. Okay. Now, for a very long time, this was a theoretical prediction of Einstein's equations around 1916. And subsequently in astrophysics, black holes have been seen in various indirect ways. But the first direct observation of a supermassive black hole was done very recently by the Event Horizon Telescope. And this is a very famous picture. And you see this black spot in the middle, which basically is telling you that there is no light observed coming from the line of sight, actually. So this is a very beautiful story. You can look it up on the internet. And black holes have also been observed indirectly in various circumstances, especially by Guess and Genzel. They observed indirectly the massive black hole in the middle of the Milky Way galaxy, and also indirectly by the collision of two black holes which set off gravitational waves which were observed by LIGO in 2014 or 15 or something like that. Okay, good. So they are real. So they are important objects of study. All right. Now we go back to theory. So around 1970s, Hawking proved what are called the area theorems of general relativity. So you take two black holes, okay, of some horizon radius, which characterizes them, or some mass, and you coalesce them slowly, okay, and they become a bigger black hole. Now, and in order to conserve energy, of course, some gravitational radiation is given out. Now, the area theorem says that the area of the final black hole is always greater than the sum of the areas of the initial black holes. So a black hole cannot split apart, and hence the reverse process is impossible. This is a very beautiful geometric theorem, very general theorem based on Einstein's general theory of relativity. Now, with this in mind and some other ideas, Jacob Bekenstein in 1973 made a very beautiful proposal in order to reconcile black holes with the second law of thermodynamics. So he said, take a black hole, take a bucket of hot water and throw it inside. It disappears classically. And therefore, it decreases the entropy of the universe and therefore violates the second law of thermodynamics. So this is a contradiction which Bekenstein said can be avoided if one attributes a thermodynamic entropy to a black hole which is proportional to the area of the horizon, keeping in mind the area theorems of Hawking. Well, that's a big step forward to connect general relativity with thermodynamics. And so Bekenstein proposed that the area of the horizon is proportional to the entropy of the black hole, okay, as we have said. But this constant, this is $1 million question. What is this constant? And I'll tell you about this constant a bit later, actually. It cannot be determined in classical physics. And so, as I said, the area theorems imply the second law for the generalized, what is called a coarse-grained thermodynamic entropy, which we in engineering, in classical engineering, are all familiar with. Okay, and the generalized entropy, they introduce you have to talk about a black hole of the entropy of the black hole, but all the stuff that is outside it also. So it's a total entropy which satisfies the second law of thermodynamics. And this is called the generalized entropy, is a central player of our talk, and I'll come back to it later. And the second law of thermodynamics for this generalized entropy was actually proved very recently by Aaron Wall. So therefore, when the hot water bucket falls into the black hole, as matter decreases, but the entropy of the black hole increases, and by more, to satisfy the second law of thermodynamics. Okay? All right. Let's move on to the second part of our talk. So now we introduce quantum mechanics, Hawking radiation, and that leads to the information puzzle. Okay, so in one of the celebrated calculations of the second half of the 20th century, Stephen Hawking discovered that black holes radiate due to quantum effects. He calculated the temperature of the black hole and found his famous formula, which is on his tombstone. So here is a picture of Hawking celebrating his birthday during his visit to the Tata Institute in Mumbai on the occasion of Strings 2001. So this is the famous formula of Hawking. This is really a centerpiece formula. It says the temperature of the black hole is proportional to Planck's constant first, okay, and is inversely proportional to the mass of the black hole. So, for example, if you plug in over here mass of the sun, which I'm sure all of you know, you'll get a number like 10 to the minus 7 Kelvin, which is very tiny, not observable. If you introduce the mass of the Earth, you'll get something like 0.1 Kelvin. And however, if you reduce the mass further, the temperature is very high. So just to give an idea of the numbers involved in this formula. And most fundamentally, this formula is proportional to Planck's constant. So it's purely quantum mechanical. This is the point. Now we take this temperature entropy connection, substitute in the first law of thermodynamics, and you got the famous formula of Bekenstein and Hawking, in which the constant B now turns out to be 1/4. I don't think 1/4 was ever sought after so much in the history of science. This number is crucial, actually, to give you the right formula, and it comes from quantum mechanics. Okay, all right. This is Hawking. Now, why is the calculation of Hawking so important and universal, actually? why is the temperature and the entropy that formula on the last slide showed you so universal? And I can't explain this to you very in great detail, but here is a glimpse of it. The formula for black hole temperature and entropy is universal and independent of how the black hole formed. It's independent. And this is because the answer at late times, these are the late times at which an observer is sitting here with a apparatus looking at the radiation. At late times, only very high energy Hawking quanta, Hawking radiation modes from around here, even after the black hole has gone in, actually, this is the horizon, essentially make a contribution to the calculation of the black hole entropy. Now, there's a very beautiful and lucid explanation of all this given by a recent talk of Edward Witten at the Madan Lal Mehta lectures of the TIFR. Okay, so black hole temperature and entropy is universal. Now, there's one more point. The radiation that comes out appears to be thermal. And it appears to be thermal because we are not keeping track of the part that is already on the other side of the horizon. Remember I said space-time has two parts, outside the horizon and inside the horizon. If you look at the radiation only in the outside, then clearly you will get a thermal answer. And this is the reason why you're getting a black hole temperature. This is the reason why you're getting an entropy, etc., etc. Okay. So this is a statement about the universality of those formulas. Okay. Now, given this great calculation of Hawking, it creates trouble. The trouble was first announced by Hawking. Hawking believed that quantum mechanics will have to be modified and not general relativity because of what I'm just about to say. So like all hot bodies, black holes radiate. So a black hole forms in various ways, as I said, but it always evaporates in the same way, into thermal radiation, okay, and leading to information loss. Because now, once it evaporates, there's no memory of how it was formed. The state which formed it, there is no memory of it. And this particular point violates a very fundamental principle of quantum mechanics, the principle of unitarity, that probabilities or states, or a state which is pure means a given quantum state, cannot go into another state which is a mixed quantum state, which sort of is thermal. This is a little technical, but I'll try to elaborate a little bit more a bit later. But this is what it is. So we have a serious problem. This serious problem was first raised very shortly after Hawking's famous paper of 1975. And that general relativity leads to information loss, but quantum mechanics cannot allow it. So therefore, the two very well understood, experimentally verified in their domains, theories of 20th century physics, that is quantum mechanics and general relativity, are not compatible when applied to this particular solutions of Einstein's equations, and for other reasons also, which has to do with short distance behavior. So this is a crisis. Many people, very famous people, call it a crisis of theoretical physics, but it also presented an opportunity for progress, especially progress in a subject which is not supported very strongly by experiments today. The experiments are hard to do. Okay, so now we come to resolving the information puzzle by black hole microstates. Okay, so this is one attempt to resolve the information puzzle, which is more or less from 1990s onwards. There's a long history to it all, and I'll just summarize it in one slide. Now, since it is established that the black hole is a thermodynamic system, it has temperature and entropy, can information loss for black holes be understood as like an statistical mechanics due to an averaging process of many internal states, like, for example, the burning of a piece of wood. Clearly, you don't jump up and down that quantum mechanics is violated, because you're doing statistical averaging, coarse-graining the system to describe it in the language of statistical thermodynamics, etc. So the main question was, is there a theory of quantum gravity in which black hole entropy, formula due to Bekenstein and Hawking, is equal to Boltzmann's formula? Is there a formula like this, which is on this slide? S black hole is equal to K, which is Boltzmann's constant, times log of the number of degrees of freedom of the system. Now, what are the internal states of the black hole that would account for black hole entropy? This is a fantastic development, in fact, and it's perhaps one of the success. The answer to this question is yes. And because the answer to this question is yes, it vindicates the fact that string theory is the correct theory of quantum gravity. So in 1996, Strominger and Waffa provided the first concrete evidence in a calculable supersymmetric model, toy type of model, that black hole space-time is a sort of hydrodynamic description of more basic underlying quantum system of d-branes in string theory. So string theory has more degrees of freedom than gravitons. It has these domain wall type of solutions. Okay, domain walls, people understand in many parts of physics. They are called d-branes for special properties they have, which were discovered by Joe Polchinski. And what Waffa and Strominger did is that they engineered, using these microstates, these basic degrees of freedom, an object which had all the properties of a black hole. Fantastic. I think this was a turning point, actually, of, at least in my opinion, of the fact that we should take string theory very seriously, because it accounts for black hole entropy. Okay. Then once this model was given, Hawking radiation, black hole thermodynamics, and all those things can be calculated in this framework. It took a while to do that. And if you want to read it, there is a physics report, longish review by some of us, Justin David, who is now at Indian Institute of Science, Gautam Mandal in Tata Institute, Mumbai, and myself here in Bangalore, because I was in Mumbai at that time. But this report actually summarizes this whole development and also our contribution. High order corrections, which vindicate string theory to black hole entropy were computed by Atish Davolkar, Ashok Sen, and many other people in the framework of string theory, consolidating our belief that this is the right theory of quantum gravity. And these developments gave an enormous evidence that string theory, the next big thing I'm going to talk about, is the correct theory, and led to the holographic description of quantum gravity. Now, what is that? What is that? So holographic description of quantum gravity, which was invented by Juan Mallasena in 1997, says that if you look at a theory of quantum gravity with all its complexities, in a certain space-time, a hyperbolic space-time, which is like a box, basically. It's like a geometrical box. Even everything that is going on inside has a holographic projection on the boundary. And this is the famous holographic conjecture, which has kept everybody busy for the last 20, 25 years. Given this, the information puzzle is in principle solved, right? Because here you have a unitary quantum field theory. Whatever the black hole does in the interior, whatever evaporates, forms, is basically holographically coded in this boundary theory, which is an ordinary quantum field theory, which is unitary. So there cannot be any information puzzle, and there isn't. And this is a big progress, actually. And here is a picture of what I'm trying to say. So this is the boundary, the red boundary. There are particles of a quantum field theory on that boundary jiggling around at some finite temperature, and this is a black hole in the interior. And so this is the picture which was given by Juan Malacena and applied to the problem of black holes by Ed Whitman. Now, the nice thing is that Hawking conceded that the information paradox is solved in principle. I think he lost a few bottles of wine, etc., to several friends of his, etc. Okay, so this is the end of the second part of the talk, in which the information puzzle can be solved by understanding the microstates of the black hole. But mind you, we have not understood what gravity is doing in the middle over here. How does gravity solve all these problems? So that is what we come to next. Okay, so this is actually in a sense, this is all an introduction of the past, but now let's go forward to very current times. There is recent progress in answering this question of the information puzzle, which I have outlined. It involves understanding information loss as quantum information loss and uses concepts from quantum information theory. In particular, the concept of quantum entanglement and its measure by the fine grain or entanglement entropy. And most important, its geometrization, a geometric formula for the fine-grained entropy. And this is the work goes from the famous work of Ryuhei Takayagi and many other people. There are very foundational contributions by all of these people, including Samir Mathur, who was a student at the Tata Institute a long time ago, and also by Subrat Raju, who is a faculty of the ICTS. And what these people actually, there's a whole huge development. There are many other people. It's a very connected community. That a good diagnostic of the fact that what would you like to compute to say that you have solved the information puzzle in a very gross sense, just like you say there's a phase transition, there's some order parameter which is zero or non-zero, something like that, something as coarse as that. So good diagnostic is what's called a Page curve. Page curve, because Don Page, a student of Stephen Hawking, invented this type of a construction, that the time evolution of the entanglement entropy, which I will discuss and define, of an entangled composite system. Okay, so the entangled composite system, like the black hole radiation system, should satisfy the Page curve. Means its entanglement entropy should actually evolve in time accordance with Page's curve, which is the direct consequence of the unitarity of quantum mechanics. And in what follows, I will give a very rough sketch of this recent development. So it's a little dense, but I have written down everything so that if you see the slides later, you might be able to catch up. So there is a very fundamental difference between thermodynamic or coarse-grained entropy and entanglement entropy of quantum mechanics. The resolution of the information puzzle, I'm repeating myself, it's important to repeat it, is enabled by thinking about black hole and radiation in the conceptual framework of quantum information theory and understanding the entanglement entropy of quantum systems is the diagnostic of quantum information loss. So the entanglement entropy is defined for any quantum system, and it's not restricted to dealing with a large number of degrees of freedom like the thermodynamic entropy, which is for once you coarse grain the information of the system, you can talk of thermodynamic entropy, but entanglement entropy is a concept which is valid even for a two-state system. Okay, So unlike the thermodynamic entropy, the entanglement entropy does not satisfy the second law of thermodynamics. It is not necessarily an increasing function of time. So for example, if you have two systems, 1 and 2, then the entanglement entropy, thermodynamic entropy of 1, 2 is always greater than that of 1 plus of 2. It's the other way around for the entanglement. Very, very important difference. And the other important point is that the thermodynamic entropy always bounds the quantum entanglement entropy. So this is just the number of log of the number of degrees of freedom. It is a bound on the entanglement entropy. Okay. Now, the entanglement entropy of a given state is 0. You have a quantum state, you compute its entanglement entropy, it is 0. And it's time independent. If you have some non-zero value, it'll evolve, remain constant under time evolution. And very importantly, if one divides a system into two parts and observes either one of them, okay, that means in some sense you trace over the states of the one system. The subsystem entanglement entropies are positive and they're equal. This is an amazing fact. And this is fantastic, that the entanglement entropy of the radiation is, as you will see, is the same as the entanglement entropy of a black hole. And this can decrease or increase in time. All right. And the entanglement entropy of system 1 and 2, time evolve, and they satisfy the page curve. Now, I have not told you what is entanglement. Now, this cannot be a course in quantum mechanics, but an entangled state. You have two systems, two-state system. An entangled state is a state like this, you see. It doesn't belong to system A or system B, okay? Unlike a state like this over here, it's a product of these two, belongs to a system A, system B. You know exactly, you can see it. Now, now there is something abstract here which was invented by von Neumann, which we all use as practitioners in quantum mechanics, is the idea of a density matrix. Density matrix is some operator which, when operating on this state, gives this state back. It's like a projection operator. So its square is itself. Okay. Now, as I said, if we do not want to observe system B, there are two systems here, A and B, we can trace over the states of system B and we get a new entanglement entropy. And this is the central object of our discussions. You have a system, it's a product of two systems. The entanglement entropy of that is obviously 0. But if you trace over one or the other, then you will definitely get entanglement entropy of one system or the other, they being equal, and their rank is not 1, that is, they don't square to themselves. Okay. So this is a tutorial on elementary quantum mechanics. And this is what is entanglement entropy. So I just want to very quickly say that it is the trace of the density matrix times its logarithm, and the trace of the density matrix is 1. It was invented by John von Neumann. If you diagonalize the density matrix, you will get a formula which looks like Shannon's formula for entropy, for classical entropy, but it's not the same. It just looks mathematically the same, but in interpretation is very different. And the key point is that the entanglement entropy of a state in quantum mechanics, of a pure state, which is not traced over or measured, is 0. A non-zero S is a measure of deviation from a maximally entangled pure state. Okay, so these are a few of the properties. This is literally doesn't change under unitary transformations. It's bounded by the log of the dimension of the number of states in the system, and the thermodynamic entropy minus the von Neumann entropy are always positive from here, and it's a measure of information loss. Okay, so given these properties, Page came up with this curve. Actually, the red curve is the Page curve. So if you start with an initial state of a quantum system, nobody has measured it or anything, and it's a, let's say it's a product of two states, two systems. Then if you follow the entanglement entropy of, let's say, one of the systems which you have not measured, then this entropy has to rise in the beginning. But it cannot rise forever. It cannot rise forever because we have that bound that the entanglement entropy cannot exceed the thermodynamic entropy. So it has to curve down. And there are some more details over here, and this is called the famous page curve. Now, Hawking calculation, which I'll describe very, very quickly later on, calculated the entanglement entropy, and it simply kept on growing. So this is Stephen Hawking's famous mistake. Okay, so let me just say that the entanglement entropy computed by Stephen Hawking simply keeps on rising beyond the thermodynamic entropy, because as the entropy of the black hole comes down over here, if this goes up, it's exceeding this object, this entropy, and therefore it has to go down. Okay, now, so this is our diagnostic. So entanglement entropy formula that computes, this is the main part of the talk, the last two slides. What is the main result? Computes the Hawking curve of an evaporating black hole. So recall our famous Bekenstein-Hawking formula, which is the area term, and which is the term corresponding to the entropy of the matter outside the black hole. Okay. It's a very nice, very finite formula actually, which is very subtle to understand, but it's there. And if you take, for example, a black hole and put a big surface around it, and some place where you can sit in a lab and measure the Hawking radiation, then you can ask yourself, apply this formula, considering the horizon as the surface that divides the space into two parts. And you compute and you get Hawking's curve over here, which is simply not correct. So this was the error of Stephen Hawking actually. How is this solved? What is the correct formula? And this is the main point I want to make, that you take the same formula as before, the area plus the entropy of the matter outside, set up the same experiment, but now the surface is dynamical. You determine this surface by a variational principle, okay, which I don't want to go into. In some sense, look at the minima of this as you change the surface. Now the surface is not at the horizon, okay, it's outside the horizon. It can go inside, it can even split, and there can be islands inside the black hole which are surrounded by this surface. So very complicated type of things can happen. People have thought deeply about this, and it's something I cannot really explain, except that the surface is now different. It's not the horizon, and it has to be dynamically determined from the same formula. And this was done by Pennington, Almaeri, Engelhardt, Marolf, and Maxwell in 2019. I just wanted to say that Pennington, Almaeri, Engelhardt, and Maxwell were all postdocs or young assistant professors who have really solved this, made progress. In physics, you never completely solve anything, made progress to solve this problem. And so if you take this recipe, it's not a recipe actually, it's something which you can prove, but I don't want to go into it. And you compute now the page curve, you get the red curve actually. And this is the key point, that it's the same formula as before, but the surface is different. It's not the horizon, but the surface which is dynamically determined, which accords with the page curve. So this, I think, is a wonderful development. So in summary, we have reviewed a particular promising development in theoretical physics, which brings us closer to a reconciliation of quantum mechanics and general relativity within semi-classical gravity. And this has been enabled by a new gravity formula for the entanglement entropy. Now, explicit verification of the page curve has been done in low dimensional systems. And in this talk, I have not included the following topics. I have not discussed the interior of the black hole and its imprint on the Hawking radiation and the problem of non-locality in quantum gravity. I have not discussed wormhole geometries and entanglement entropy, which is another important subject. And I have not discussed explicit dynamical evolution models of black hole formation and evaporation. Detailed dynamical models in lower dimensional systems like the SYK model of random spins, which is holographic to two-dimensional gravity, which is the work that we have been doing for the last several years. And not at the time to do that. So now, in the end, one of the reasons to study black holes is to understand the principles and degrees of freedom of quantum gravity and develop a framework to discuss the quantum nature of the cosmological event horizon, which also has a characteristic temperature and Hawking radiation. This is my last slide. The president of the academy gave a fantastic talk talking about human evolution. Here is the human being, and the universe has cooled down so much. And in a very deep sense, what we are discussing in string theory is an evolution that began much further past in the history of our universe, approximately over 13 billion years ago. And it's a very humbling thought, actually, that ultimately it's something that started almost from nothing. And with that, I'd like to end my talk. Thank you for your attention.
Thank you, Spenta, for the lucid and enjoyable talk. We have run over time, but we will have one quick question from Professor Bhaskaran and a comment. Sure. Spenta, it was a fantastic talk. Recent developments of analog quantum gravity in condensed matter systems gives a way to measure and confirm entanglement entropy idea quantitatively. Your comments, please.
Okay, Bhaskaran, I am not aware of, I don't follow your question completely, but I think you're talking only of condensed matter systems which are not dual to any gravitational system. So you're saying that there is a quantitative measurement and understanding of entanglement entropy in those systems. I am not fully conversant with that literature, but it's fantastic to hear.
All right. Thank you, Spenta. There are many praising remarks about your talk today. It's a great way to get started the day. And
thank you.
The Academy, many thanks once again. Thank you.
Thank you so much.